You know that feeling when you're staring at a physics formula and you just know you've made a mistake, but you can't figure out where? Well, it turns out physicists have a secret weapon for that exact situation. It's the simple, elegant trick for checking their work, spotting errors, and even remembering formulas they've completely forgotten. And today, we're going to learn it. Okay, so picture this. You're sitting in an exam, the clock's taken away, and you need the area of a circle, but your mind just goes totally blank. Two formulas pop in your head, these two right here. But which one is it? But what if I told you that you could figure it out right then and there, without a textbook, without having to guess? Yeah, there's a really powerful logic check that can save you, and it's called dimensional analysis. So what in the world is a dimension? Well, think of it this way. A unit is something specific, like a meter or a foot or a mile. But the dimension they all share is just length. Dimensional analysis lets us zoom out and forget about the specific units and focus on that fundamental quality. These base quantities you see here are like the primary colors of physics. Pretty much everything we can measure is built from just a handful of these. We use a capital L for length, an M for mass, and a T for time. And really, for today, those three are the main ones we're going to need. And this is where it gets really, really cool. Every other physical quantity, I don't care how complicated it seems, is just some combination of these fundamental building blocks. Let me show you what I mean. Let's take speed. What is it really? Well, it's the distance you travel, that's a length, over a certain amount of time. So its dimension is simply length divided by time. We write that as L over T, or if you want to be fancy, LT to the minus 1. And what about area? Well, that's just one length multiplied by another length. So its dimension is L times L, or L squared. Simple, right? This one little idea is the absolute key. Now let's get to the rules that make it so powerful. So we've got our building blocks. Now we need the rules of the game. And the great thing is, there are really only two core principles that make this entire system work, and they are shockingly simple. The first rule is the big one, the absolute foundation. Every single piece of an equation that you are adding or subtracting has to have the exact same dimensions. The second rule is a little more specific. If you're plugging a value into a function, say sine or a logarithm, that value has to be a pure number with no dimensions at all. And that first rule really just boils down to that old saying, right? You can't add apples and oranges. It's just common sense. You can't add 5 meters to 10 kilograms and get anything meaningful. In physics, you can't add a length to a time. Every term in your equation has to be the same kind of fruit. Okay, enough theory. Let's take that rule and go back to our exam question. We are looking for the formula for area. And we now know that the dimension of any area in the universe must be length squared, or L squared. So which one of our formulas actually gives us that? Let's break them both down. On the left, we've got 2 pi r. Now the numbers 2 and pi, they're dimensionless. They're just pure numbers, so we can ignore them. The radius, r, well, that's a length, so its dimension is L. That means the dimension of 2 pi r is just L. Now look at the right, pi r squared. Again, pi is just a number, the radius r is a length, L, and we're squaring it, so we get L squared. Bingo. So just think about what we just did. The formula 2 pi r has the dimension of length, so it has to be the circumference, right? The only formula with the dimension of area is pi r squared. We just solved our problem not with memorization, but with pure logic. Now, you might be thinking, okay, that's a cute trick for geometry, but what about the really hairy, complex equations you see in a real physics class? And the answer is absolutely yes. In fact, that's where this trick becomes a real lifesaver. Let's put this to the test with a classic from kinematics. Here, S is displacement, that's a length. V is velocity, A is acceleration, and T is time. Now, for this equation to be correct, every single term, the S, the VT, and the 0.5 AT squared, must all have the dimension of length. So let's check it term by term. The S on the left, that's displacement, so its dimension is obviously length L. Now the VT term. We multiply the dimension of velocity, which is LT negative 1, by the dimension of time, T. The T negative 1 and the T cancel each other out, leaving us with just L. Perfect. And the last term, the number 0.5 is dimensionless. Acceleration is LT negative 2, and time squared is T squared. Again, the T negative 2 and the T squared cancel, leaving just L. And look at that. L, L, and L. Every single term simplifies down to the dimension of length. That means the equation is dimensionally consistent. It's a valid physical statement. You can actually add these things together because they're all the same kind of thing. But what happens if you've got a typo in your notes, or you just plain misremember the formula? Let's say you wrote this version down, where the powers of t are swapped around. Can dimensional analysis save us here? Let's run the check one more time. S is still length, L, but VT squared, that becomes LT minus 1 times T squared, which gives us LT, whoa, and 0.5 AT becomes LT minus 2 times T, which simplifies to LT minus 1. Oh man, none of the terms match. We're trying to add a length to a length time to a length per time. This is the physical equivalent of adding apples, oranges, and, I don't know, car batteries. It is completely, physically meaningless. And as the source material points out, the technical term that physicists use for an equation that's dimensionally inconsistent like this is, quite simply, nonsense. So you see, this is way more than just a neat trick. It's a practical tool. It's your new superpower. Let's talk about how you can actually use it. This is your new toolkit. You can use it to spot typos in textbooks or things you find online. You can use it to jog your memory and figure out the basic form of a formula during a test. And maybe most importantly, after you've done some long, messy algebra, you can use this as a final sanity check to see if your answer could even possibly be correct. It's an amazing error detection tool. And this all leaves us with a final, much deeper thought. The fact that any true statement about our physical reality must be dimensionally consistent is kind of remarkable. It suggests there's this deep, underlying logical structure to the entire universe. Why should reality be so neat and tidy? That's something to think about.